Awesome. Hello and welcome to today's discussion of the Lynn Lab's recent paper, Electrochemical Azidooxygenation of Alkenes Mediated by a Tempoazide Charge Transfer Complex. We're here today with Juno, one of the authors of the paper, to talk about what it was like to work on this project and how they feel now that it's sort of published and they're moving on to other things. So welcome, Juno. Before we get started talking about the paper, why don't you tell us a little bit about yourself?
My name is Juno, and I'm from Hong Kong. I did my undergrad in England at UCL, and at the time, I was raised as an electrochemist actually, but I was really interested in organic chemistry too because I found the arrow pushing and the mechanistic study part of it very interesting. And then so I did really well in organic chemistry, but I didn't have any organic synthesis background at all, like no practical experience. I only know how to do, rotating disc electrodes and CVs and all of that stuff. But then I found it very interesting with Song's work after a meeting with him during recruitment weekend. So I decided to, join Song's group, and here I am. I'm fourth year now, and I'm really pleased with the work that we've done, and I really like working with Song, and this was the first project that we have completed in the lab.
And this is an awesome paper, and this is an awesome project. And if you haven't read it yet, you definitely should get a look. It's on the screen so that you can sort of follow along with our discussion. And the thing I always like to learn about projects like this is, where did the idea come from? Did it just like come born from nothing, or can you tell us the story about sort of the beginnings?
Yeah, so this project was discovered completely by accident. And originally, this was actually just a control reaction that was used in the very first paper, the science paper on the manganese diazidation. And as you can see from that paper, there's only one entry there where we use tempo as an additive to support a radical intermediacy of the reaction system. So it's mainly just a control reaction. But then it turned out to be quite a useful and high yielding reaction. Like, it works for a variety of alkenes, and we can get like vicinally CN and CO functionalized products in high yields. And as a first year, Song was trying to let me build confidence and to work on something that is easier and will result in a publication, and probably like in JOC or something. But then we followed one thing that didn't make sense in the mechanistic proposal, and that led to a 10-month long project on this. So we followed this single color that was observed in the solution that was dark red. So the dark red color immediately forms when you start electrolyzing the reaction. And that was not consistent with our simple mechanistic proposal that we're directly oxidizing azide to azidyl radicals, and then tempo acting merely as a persistent radical trap for the C-center radical. So that didn't make any sense, because none of those intermediates would have given that spectacular color change. And following that color change gave rise to all of this project. And pleased to discover this new charge transfer complex. Yes,
that's fantastic. Some simple observation in lab leading to a huge new discovery. That's fantastic. That's really good science. And I was wondering if you could tell me, what was your favorite part about working on this project?
Well, I'm a very curious person, and I really like understanding the mechanism, and the gradual revelation of the mechanism as you do more and more experiments was very rewarding. And it's almost like a detective, going around asking people things, and then, oh, how did this murder happen or something? And then you quickly, gradually nail down, oh, it has to be like this person or something. And though in mechanisms, you can never prove a mechanism, but you can definitely do experiments to eliminate other possibilities. And by Occam's razor, the simplest mechanism that is consistent with all the experimental evidence is most likely the mechanism, right? And I
I
find that very fun.
and it comes through so well in the paper, a passion for understanding the mechanism of this transition.
Hmm.
So that's really nice to hear. But I'm sure it wasn't all sunshine and roses. I mean, no
Yeah,
project.
yeah.
What was there ever a time when you were working on this when things were tough, and what did you do to sort of push past that?
Hmm. So I'm kind of an empiricist as well. Like I like doing practical things, and this project, like the products are useful to the pharmaceutical companies, and doing useful things keeps me going during difficult times as well. Like knowing that one day my discoveries or invention is gonna somehow benefit society. That's part of the driving force that I have and keeps me coming to work every day. Yeah.
Yeah, that's definitely important. Um, and it's good
Yeah.
to hear and to know that your research is valued.
Yeah.
Definitely.
And
Yeah.
also I want to add is that I like to keep like little goals every day. I make a small, sticky notes with like 3 or 4 things that I need to complete on a daily basis. So I like crossing them out when I'm done with them. Just like very little goals, like
Yeah.
purifying this reaction or like isolating this compound and or doing a 2D NMR on this sample. Like little goals keep you in track and also give you kind of a sense of like achievement and progression in times that there are not so many good results. You feel way more efficient and you feel much better if you keep crossing out things on the list. I love doing that.
Crossing out things on the list is one of the best parts about,
Yeah.
the lab every day, for
Mhm.
sure. And one thing that I like about this paper in particular is that, you look at the author list and you see like such a large group of people,
Mhm.
from different sort of research groups also. And I was wondering what it was like to work on such a collaborative team.
So I like working with different people, and two of the authors there, Amber New and Reed, they're both my undergrads, and then we talk extensively in the lab, not just about science, but like we share a lot of personal stories and personal things, and I really like doing that because it feels like that we're connected and that we're really good friends and just makes things a lot easier than working with like a stranger and where you just only talk about the science. So I really like to get to know every author personally. And Greg was, also a second year back then, and we were in the same cohort, so we knew each other and we talked about all kinds of things. Yeah.
That's fantastic. I love projects that exhibit mentorship. I love projects that are very collegial. So it's definitely good to see, how rewarding it can be, with a paper like this. And so, when you look at a work like this, you've got a lot of substrates, you've got a lot of things that you learn. Is there one key takeaway or one like piece of data that you're the most proud of from this paper?
Yes, definitely. So if you scroll down near to the end of the paper, where there is a substrate, I think it's 2Y, it has a pendant alcohol motif on it. Yeah, it's a pretty long paper.
But worth the read. Definitely worth the read.
Yeah.
There it
Yep.
is.
So here it is. Yeah. So the substrate 2Y, as you can see, it has a primary alcohol on it. And as you probably know that, you know, oxoammonium, so the oxidized version of tempo, is very capable of oxidizing, alcohol to the aldehyde. It's a,
It's like
40-year-old reaction. Everyone knows about that. And
Mhm.
yet we can achieve azidooxygenation on this substrate without touching that alcohol, it greatly shows that this charge transfer complex does exist, and it prevents it from doing the normal chemistry that it does, and it instead does something completely orthogonal to that. And that kind of solidified our discovery and showing that kinetics is kind of on our side as well.
Yeah, it's like a double whammy as both like mechanistic probe, but also being
Yeah.
a cool highlight of how sensitive your methodology is. And,
Yeah, this substrate was added only after we knew about the reaction mechanism, and we thought, based on this proposal, maybe we can, put in substrates that previously was thought to be impossible. That really highlights the work that our lab does, which is to understand the mechanism really well and use that knowledge to leverage a larger, more interesting substrate scope.
yeah, well, it's definitely awesome work. And in a paper like this, you go into the review process, I imagine, with a little bit of like trepidation, just because there's so much material. Do you have a story about the review process, about how it made the paper better, or an experiment the reviewer asked you to do that at first you grumbled about, but at the end sort of made things a little bit better?
hmm So if you move up a little bit the paper to where we summarize the whole mechanism, the reviewer was actually incredibly smart. Like that reviewer, in my opinion, it might have been Donna Blackman or something,
Mhm.
who has very, very sharp sense of like mechanistic study. And he or she asked, have you considered our proposed mechanism as kind of like an off-cycle um, reservoir of azidyl radicals. So instead of putting it in a linear fashion like this, could this charge transfer complex just merely act as a off-cycle reservoir of azidyl radicals? And that proposal was completely valid and consistent with all the experimental evidence. And in fact, we thought about it for a very long time, and we couldn't come up with an experiment that could differentiate both these pathways.
Mhm.
And the reviewer didn't come up with an experiment to differentiate it either. But it's just a very valid proposal. So I was really frustrated because we couldn't do anything about it. But now that it's been published, and then another follow-on project has also been published on this charge transfer complex, we confidently know that this isn't the case anymore, because we can do a catalytic diazidation as well. So it had to be on cycle and not merely an off cycle reservoir. But that conclusion came out after the second paper, not from this paper. And luckily, the reviewer, the editor, allowed us to put this mechanism instead, which on paper looks cooler than an off-cycle reservoir. Yeah.
Yeah. Well, that sort of nicely leads into my final question, which
Mhm.
is there a key lesson or a takeaway that you learned from this project that you're carrying forward into your current work?
Yes. So a big principle that I always follow by is like, don't neglect those um, minor side products in a
Mm.
reaction. Whenever you're trying a new reaction, or even just going through substrate scope, sometimes there are some small, just 5 to 10% of this side product you think is kind of unimportant, but all my papers, the best ones, they all came from like isolation of a minor byproduct. So don't neglect them.
Yeah.
They tell you so much about a reaction. And you know, my next paper, the diazidation using also nitroxyl radicals, is also from one of the substrate in this paper, which I've isolated like a small percentage of the diazide, which we weren't expecting and could not be explained by free radical dimerizations.
Mhm.
So this is a very good lesson that I learned, and I have kept this principle till now, like always isolate minor side products. They tell you so much. And don't be lazy. Like if a reaction even converts a little bit to something else, even if it's something that you don't want or don't expect, analyze it. Spend the time to do 2D to analyze what it is. Yep.
That's great advice, and it's good. It's a good lesson for us all to think about for our own chemistry too. So I guess thank you for taking the time to chat with me. I know it's over Zoom because of the current COVID situation, but it's been really nice to talk about your paper, and I hope to talk to you about your next paper soon. And thank you all for tuning in, and hopefully you get a chance to read this paper, and hopefully you'll hear from us again soon to talk about the next one. So thank you, Juno.
Thank you, James.
Yeah, take care.
Bye-bye.